have solid ammonium chloride, solid NH4Cl, was placed in an evacuated chamber. Then heated. It decomposed according to NH4Cl solid decomposes into ammonia, NH3 gas, plus hydrogen chloride gas. It's not hydrochloric acid, it's hydrogen chloride gas. Okay. Now, after heating, the total pressure was found to be 4.4 atmospheres. 4.4 atmospheres. Our task is to calculate the Kp, the equilibrium constant with respect to pressures. Okay. Well, let's write out the equilibrium expression first. It's always a great thing to do. Write everything out. Write out the equilibrium expression, write out the ice chart, and then just see where you go from there. So, the equilibrium expression here, based on this equation, well, we have a gas, and we have a solid. Solids don't show up in the equilibrium expression. So in this case, it's just these two. The coefficients are 1. So we have the Kp is equal to the partial pressure of NH3 gas times the partial pressure of HCl gas. That's it. If we find the partial pressures, we're done. We plug them in, we multiply them, and we're done. Okay, now let's do our ice chart. Do our ice chart, always do it this way. NH4Cl, write out the equation and do it underneath. Don't do it separate. You want to be able to keep everything straight. Goes to NH3 plus HCl. Our initial concentration, our change, and our equilibrium concentration. Okay, solid NHCl, we don't care. Doesn't even matter. So we just put lines there. Doesn't show up in the equilibrium expression, doesn't matter. Our initial NH3 and HCl concentration, well, we started off with solid NH4Cl, so initially there's none of these. The change, well, a certain amount shows up. That certain amount is what we want. So plus X, right? So again, you have to see what the question is saying. It's telling you that you start off with NH4Cl. It decomposes. When something decomposes, that means it's going away. The products are showing up. So that's why you have a plus X and a plus X here. This plus goes here, it's not that plus. 0 plus X is plus X. 0 plus X is plus X. Well, they're telling me that the total pressure in this flask is 4.4 atmospheres. Well, which gases are in the flask? Well, the solid is a solid. That doesn't matter. That doesn't do anything for the gas. The gases in here are NH3 gas and HCl gas. So I basically have X plus X is equal to 4.4. They're telling me that the total pressure in there is 4.4 atmospheres. That has to be made up of the amount of NH3 gas and the amount of HCl gas. Well, that's even because they're forming in 1-to-1 ratio. So 2X is equal to 4.4. X is equal to 2.2. Well, 2.2, there you go. That's the partial pressure of HCl and the partial pressure of NH3. I have 2.2 and 2.2, not 2.4. Numbers and arithmetic. These numbers are the ones that I put back in here. So Kp is equal to 2.2 times Okay, now watch this. Even though 2.2 and 2.2 is the same, please don't write 2.2 squared. They're different species. I promise you. If you write 2.2 squared, and if somewhere along the way you get lost and you have to come back, you'll spend 5 minutes trying to figure out what happened. Because again, stoichiometric coefficients, they show up in the equation. So write them separately. Write 2.2 times 2.2. Even though they're the same, they represent different species. Don't mix them up. So we multiply that, we get 4.84. 4.84, that is the KP. And we double check, calculate KP, that's what we wanted. We're done. That's it. So they gave us a certain amount of information. They gave us an equation to work with. We wrote down the KP expression. We wrote down the equation. We wrote an ice chart, initial, change, equilibrium. Ultimately, it's the equilibrium that we're concerned with because the system has come to equilibrium. We followed it. We get X and X. They tell us that the total pressure is 4.4. Well, the total pressure is the sum of the individual pressures. There's only two gases in here, the NH3 and the HCl. Each one is X. 2X equals 4.4. X equals 2.2. At equilibrium, 2.2 atmospheres is hydrogen chloride gas. 2.2 atmospheres is ammonia gas. We plug that into the equilibrium expression. We multiply, and we get 4.84. Standard equilibrium problem. Okay. This sort of gets us going with the types of problems we're going to be dealing with equilibrium. We are going to systematize this, and this whole idea of the ice chart, our problems are going to start to become a little bit more complex, but this whole idea of using an ice chart, writing the equilibrium expression, and then seeing what they want based on what they give us, the ice chart itself is going to be different. That's what's going to change. The approach is not change. Okay, so thank you for joining us here at Educator.com for AP Chemistry and Equilibrium. We'll see you next time.